Okay, so this video is about how to use the parallax method for measuring distance to stars. Okay, so here's our diagram I'm going to use to explain this. It's quite a complicated one, so I'm going to run you through it in a lot of detail. We've got the Sun here and the Earth and the orbit of the Earth shown. And I've labelled this distance 1 AU, which is called an astronomical unit, and approximately that's the radius of the Earth's orbit. I say approximately because obviously the Earth's orbit is elliptical, or slightly elliptical, so it's not got a constant distance from the Sun. But we don't need to worry ourselves about the technical details of the definition of the astronomical unit. It's roughly the radius of the Earth's orbit. Okay, so what is stellar parallax? Well, it's the apparent shift of a nearby star against the fixed background of distant stars. Now, obviously the term nearby for describing stars is relative, as is the term distant. So we're going to show it on this diagram here that this is the nearby star in the centre here, and the distant stars are these ones off on the right hand side. And the thing we have to really point out about this diagram is nowhere close to scale. Obviously in the real situation, the star on the scale of the Sun and the Earth here would be millions of times further away, and as a result of that the angles we're going to measure for this shift would be millions of times smaller than the ones you can see here. But obviously if we're going to see it in a diagram, we have to have an angle that we can actually notice. Otherwise it's not very helpful for understanding what's happening. But you must understand also that the real angles are much smaller because the real stars are much further away. Okay, so the green box at the top here is a view of what we would actually see on Earth, looking from the Earth towards this nearby star at these background of distant stars. And I've put the distant stars on to start with. Now, bearing in mind that the main view here is kind of like a plan view. We're looking down on the solar system and down on these stars from some sort of distant viewpoint. So you can see that I've put this white double arrow on here. That's to represent what the direction correspondence between what we see on Earth and this diagram here. So you can see that the left right in this green box, which represents what we see on Earth, is the same as the up down on the main diagram here. And so looking from left to right on what we see on Earth, we can see this orange star here corresponds to the orange star at the top here. There's a white star here corresponding to that one, and then a yellow and white close to each other corresponding to these two here, and then a red and yellow slightly further separated. Now obviously the height of these stars in this green box, how far they are up the green box, we cannot see in this view because it's a plan. Okay, all we're really interested in is how much the nearby star shifts against the background, and we're going to see how that works now. So what we do is we have the Earth in one position. I'm going to run the animation and show you what happens. We have the Earth, say, in January, okay, and then this dotted line shows us where the nearby star appears in comparison to the distant stars, and the dotted line runs directly from the Earth through the nearby star towards the distant stars. And you can see that the dotted line goes between the red and yellow stars here. That means that in the left-right sense, as from what we see on Earth, this is the position of this nearby star in January. We've put it on the diagram now and marked it so it's really clear. And then what we do is we let the Earth continue in its orbit for 6 months, and we're going to see it orbit all the way around. And during this you're also going to see how the position of this star shifts against the background. Okay, we're going to mark the extreme positions at 6 months later, so the Earth in July, and where the star appears in the background at that point. So I'm going to run the animation, watch carefully. Okay, there's the Earth orbiting. You can see the star shifting, marked the extreme position, and then it shifts back. Now, obviously, actually, in the latter half of the Earth's orbit, we wouldn't really be able to see the star at all because that would be daytime on the Earth. So we can only really see it in this first half of the arc. I've marked the shift back again anyway, just so you can see what's going on. So there's the amount of shift, and I've also marked this angle here between these two dotted lines. Now in practice, of course, when we're measuring this, you would use what this green box shows. And if you remember, stellar coordinates are measured in right ascension and declination, and it would be a change in this case if it's going across the horizon in right ascension. So you'd be able to measure this angle by using the stellar coordinates. Okay, so what we then see, right, is that we can use this angle to calculate the distance to the nearby star. We call this angle 2p, where p is this thing called the parallax angle. So actually the parallax angle will be formed by the right angled triangle between this 1AU line here, the dotted line to the star, and the line back to the centre of the Sun. Okay, but suffice it to say that if you have this full angle marked here, it's twice the parallax angle. It's often forgotten when doing these calculations. Okay, and then we define the distance in this unit called parsecs, which stands for per arc second, as 1 divided by the parallax angle. Okay, now 1 arc second is 1/3600th of a degree, which is obviously a very, very small angle. So it gives you an appreciation for how small the angles we are dealing with are here, that typical parallax angles for stars are much less than an arc second, even for nearby stars, so much less than 1/3600th of a degree. So that's the principle. I'm just going to run you through one example of a calculation using this idea, and then some limitations on this method of measurement as well. So here's our diagram simplified with all the extra stuff stripped out, and all I've done is I labelled this measured angle in degrees of 0.000185 degrees, a tiny, tiny angle. Okay. So what we do to calculate the distance to the star in parsecs is, first of all, we need the angle in arc seconds. You may be given it in arc seconds, or you may be given it in degrees. If you're given it in degrees, convert by multiplying by 3600. That gives us 0.666, or 2/3 of an arc second. Remember that that angle we've marked is twice the parallax angle, so we've got to divide it by 2 to get the parallax angle. That takes us to 1/3 of an arc second. And then we apply the formula that the distance is 1 divided by 0.333, which is 3 parsecs, and you write that as 3 PC in the abbreviated form. So that's the method for measuring for actually doing the distance calculation. Just check, your units. You may not need to convert to arc seconds if you're already given it. They may directly give you the parallax angle rather than twice the parallax angle. Just watch out for those things. Okay, so what are the limitations and comments on this? Just in terms of how large these distances are, a parsec is similar in size to a light year. In fact, 1 parsec is just over 3 light years. In terms of its relationship to the astronomical unit here, just to give you an idea, that the parsec is about 200,000 astronomical units. Okay, so that gives you an idea of how much further apart stars are than the planets are around them. Okay. Now, the range of this technique is obviously limited by our ability to measure angles. That makes sense. We need to measure very, very small angles. As the star gets further away, the angle gets even smaller. And, the best measurements of this are done by orbital telescopes, which avoid the sort of a distortion in the atmosphere due to convection currents, okay, refracting the light in the atmosphere. And there's a satellite called Hipparcos launched in 1989 that got decent parallax measurements up to about 1,000 parsecs away, and by decent I mean sort of accuracy of about 10%. There's another satellite at the moment called Gaia, which is doing a bigger survey, which with better precision, which should be able to get to about 10,000 parsecs. And for comparison's sake, to give you an idea of how much of the galaxy we can map using this technique at present, the whole galaxy is about 30,000 parsecs across. So Gaia should be able to look at a reasonable chunk of it, but up till now we're talking tiny, tiny fractions of the whole, even our galaxy mapped using this method. So it has its limitations, but it is useful for calibrating other techniques. If you watched the video about Cepheid variables, you'll see that one of the ways we can calibrate Cepheid variables is by using a parallax measurement of the Cepheid variables that are relatively near to us. So that's parallax and its limitations, uses. Hopefully that's been useful.